OK, so now we're going to talk about how to implement mutual exclusion without atomic operations. So actually, I'll ask here, how many people have seen mutual exclusion without atomic operations before? OK, a few. People probably take an operating system class might have seen this before. But it's a little tricky and good to refresh anyway. So we're going to throw out test and set. We're going to throw out other things. We're going to look at how to have locks and mutual exclusion without any ordering, or without having special instructions add to our instruction set. So let's take a look at a basic piece of code here that is wrapping around a critical section, trying to implement a P and a V. And we're gonna look at the case where we only have 2 threads. The n-threaded case gets a lot more complicated. So in this simple case here, an easy way to go about doing this is, or one way we can think about doing this is, process 1 sets its variable here to 1. Then it checks to see if the other process has written its lock variable. And these are 2 different variables, C1 and C2. And we're assuming sequential consistency for this. If it sees that the other process wrote that value to 2, or to 1, C2 to 1, it says, oh, process 2 already won here. It's going to go execute its critical section. So it'll sit here and loop until C2 is set to 0 at the end of the critical section. OK, anyone see any problems here? Yeah, so if they both set their variables to 1, so if we interleave this instruction and this instruction, and then both do the checks, C1 and C2 are both going to be equal to 1. They're both going to check if, and they're going to say, OK, yeah, C2 is equal to 1, C1 is equal to 1, spin forever. None of them will ever get to their release of the semaphore. And all of a sudden, you have deadlock. That's not great. So this is why this stuff's really hard to do. So let's look at our second attempt here. Let's try to make that better by adding a little bit more checking in here. So same thing. C1 is equal to 1. C2 is equal to 1. It does the same checks to see if the other thread set the variable. And if it doesn't win, it clears its own. So it sets C1 back to 0 if it fails, and loops back up here. Well, this looks a lot better. Yeah, we're not going to get any deadlocks here, I don't think. Because let's say we're trying to interleave these things. C1 sets to 1, C2 sets to 1. They both do the check at the same time. They both say, oh, the other person grabbed it. I'll release my variable, set it to 0, and loop back around. So we don't deadlock here. And if you perturb the system a little bit, at some point, one of them is going to fall through, we'll say. But what happens if the system's not perturbed? Well, you can actually hit live lock here. Because they can just sit there, and in lockstep, if you interleave these 3 instructions with these 3 instructions here, they're going to just keep going through the loops, clearing their variables, setting their variables, clearing their variables, setting their variables, testing. And neither of these 2 processes are ever going to fall into the critical section. So live lock here is just as bad as deadlock in this case. And another bad thing here is we have no guarantees of fairness. So you could actually have a case where one process grabs this lock, we'll say. The other one sits here and loops, and it's able to execute its critical section, clear C1, get back around, set C1 before process 2 is actually able to go around this loop. Now you're going to say processors probably are not running at different speeds. Well, that's true, but maybe this one has to take more cache misses than that one, or who knows? you don't have a strong guarantee. You can't prove that one thread is not going to starve. So this is a fail. We can't have mutual exclusion this way. So instead we go and we say, well, let's make it more complicated. And this came up, was made by Dekker and is largely called Dekkers algorithm. And this is actually a protocol for mutual exclusion which works with just using modes and stores. And we introduce another variable here. And this is a shared variable between process 1 and process 2. And we call this the turn variable. So this looks pretty similar to what we had in the previous slide. But now, the turn variable is shared between the two. And what this is really going to act as is this is going to act as a tiebreaker in the case where they both set C1 effectively at the same time. And the tiebreaker is interesting here because actually this does two things. It's tiebreaker, and we'll see how it is able to solve some problems around starvation. But the turn variable, one of the two threads here, because it's a shared variable and we're sequentially consistent, is going to execute last, we'll say, either the left side or the right side. So when you come down to here and do this check, whoever raced and actually set that turn variable last, the other thread is going to execute. So let's say process 2, we interleave these and these. Process 2 now sets, process 2's turn equals 2 happens last. And when this goes to execute here, we'll see that C1 is set and turn is equal to 2. So we're just going to sit here and spin. The other thread is going to see turn equal to 2, and C2 is set. But we have a logical AND here. So both of these are not going to be true. So it's going to fall through and execute its critical section at this point. At the end, C1 is going to get cleared. And what happens here is that's going to allow this other process to enter into its critical section. So why this is nice from a starvation perspective is, at least for two processes, it's going to allow you to alternate here. Because one of them is going to enter in, and when the other one goes to clear this variable, you're guaranteed that the other one can go execute at that point. So you're not going to have starvation. Now, the reason you don't get starvation is actually kind of subtle. OK, so let's look at the starvation case. So let's say process 1's really fast. It can just loop around, and it can get around this loop and come to this point before process 2 can basically loop around here once. Is that the case you want to look at? Yeah. So what's going to happen at that point is, well, two things are going to happen. When C1 gets set to 0, what's going to happen here is process 2 will never see C1 set to 0, is what Bertrand is saying here. Because it's going to set to 0, then it's going to set to 1 before this check can happen. But what is interesting here is at some point, but C2 is still set to 1. Because this one's sitting here waiting. OK, so C2 set to 1, and turn gets set to 1. That's going to block process 2 from entering at this point. Or rather, this being 1 and that being 1 is going to block it from executing. And when turn gets set to 1, or rather, let's hold off and look at this. That's going to allow this process 1, and it's going to force this process 1 to sit here and spin forever. And it's not going to be able to go race around a second time. Process 2, on the other hand, C is going to be set to 1. Now, in the meantime, C was 1, and then it was 0, and then it was 1 again. But turn is no longer equal to 2 at this point, which is going to allow process 2 to fall through and execute its critical section. So it's this shared turn variable here, which actually allows us to guarantee, if you have a contended case, such that you're basically going to have a round robin between the two. OK, so I think we went through that. I wanted to finish up today talking about one last idea here in the last 2 minutes. You can, to do Dekkers actually with n processes, more than 2, gets pretty tricky. Dijkstra shows a proof of that. There's something that's a little bit simpler to reason about called the Leslie Lamport's bakery algorithm. And the bakery algorithm is kind of interesting because the idea is, if you've ever gone into a bakery or gone into a deli, there's the little tickets. You go in, you take a ticket, and then you wait for them either to call your number or the little number on the screen to tick up 1. And then once it ticks up, you go and you get your bread or get your sliced cheese or something. Well, you can do this with just loads and stores. You don't need locks to go implement something like that. And I don't want to go into complete detail here, but basically the idea here is you set that you want to take the lock. And then what you do is you check if all of the people below you are waiting on the lock also in order. So it's kind of like you're checking to see if the number has incremented up to you up to this point. And if everyone below you is, if there's no one below you who's waiting for a lock, then your number came up and you can go execute. But if someone is, you can't go execute this. And you wait for everyone else to release or set their variable to 1 effectively until the point that it's yours, and then you can go and buy your bread or order your cheese. Now, that's not enough to actually work. There are things called ticket-taking locks, which is actually a more general class of this sort of idea here. But you also need this sort of second matrix here to prevent sort of ABA problems with things running around. But I don't want to go into full detail about that. But I just wanted to give you an idea that one way to go implement sort of fast locks is our ticket-taking locks. You walk in, you take the ticket, and this prevents multiple people from hoarding up to the front of the bakery and all trying to order exactly at the same time. And in the bakery, it's a little bit easier because on the wall, there's like a number, and someone ticks the number up each time. If you don't have a central arbiter to go tick the number up, you need to somehow make the last person who had the lock increase the number. And that's what this algorithm is actually doing. OK, let's stop here for today. Next time, we're going to talk about symmetric multiprocessors. We're running a little bit behind where we were supposed to be from the syllabus perspective. We're about half a class behind. But I think we'll be able to pick up most of that.